What's up, guys? This is the fourth lecture of your power electronics series. Today we're going to discuss BJTs, MOSFETs, and IGBTs. This is really essential components before we start in the applications. Next week onwards, we are just jumping into the real-world applications, starting from voltage regulators and some kind of motor controllers. So before we covering and move into the applications, this lecture gives you insight to the basic devices, like we are using BJTs, MOSFETs, and IGBTs for switching devices in power electronics. So hope this lecture will be useful for you to understand the concepts easier. So BJTs, MOSFETs, IGBTs, they come in various packages, as you could see here, different packages for different power levels. So they have been used in many applications like inverters, power converters, UPS, motor control systems. Even though you might have covered a few of these concept of BJTs and MOSFETs in your first year lectures, but this lecture is more focused on power electronic applications, not like small signal amplifications of use of BJTs, but just keep your eye open and see what's real applications in BJTs in power electronics. BJTs, stand for bipolar junction transistors. They come in 3 terminal devices. You can see here the first one. You might have familiar very small BJTs like 5646 series and different kind of small. So you might have played in your undergraduate first year. We are not dealing with the small signal devices like this kind, but most of the time power electronics BJTs are for high power applications and they can come with packages like TO247 or surface mount type. The BJTs are used for mostly in power electronics as switches, but not limited for switching. There are some applications they could be still used as a mix of analog electronics. For example, now if I take this example, this is a buck converter which step down the whatever input voltage to a desired output voltage level. For example, if you consider typical 12 to 5 volt to Arduino type power supply, you can connect a 12 volt battery and you can take 5 volts output to feed your Arduino or any kind of electronic devices. So buck converters are used for step down the voltage. For the switch, this BJT is used in here. So it acts as a switch either in the on state or either in the off state based on the control signal given to its base emitter junction. There's another application for loader power regulators. Here you can see the BJT and P-type BJT is used. So it is also a step down the input voltage to output voltage. You might have seen this kind of linear regulators on top of your Arduino boards. Sometimes there's an internal linear regulator. If you're using external supply to feed your Arduino, this linear regulator will step down into the 5 volts output. So inside the linear regulator, there's a PNP type BJT. So the BJTs, they can come as PNP and NP type depending on your application. Right. This slide shows you the biasing of two types of BJTs. The first one is the NPN type. There's this base emitter junction is shown in here, and the collector emitter junction is shown here. So you have, this is the typical symbol of a NPN type BJT. So this is the base junction, comes to here. The direction of the current is shown in here. This is the emitter and this is the collector. So the base emitter voltage is represented as VPE. The collector emitter is VCE and the collector base is VCB. So whatever the current comes to the base and the collector should return from the emitter. Therefore, the emitter current should be equivalent to the sum of base and the collector current. Now here, if you want to see how this works, basically in the NPN transistor, you have to provide positive supply here and negative supply here. This could be done using a simple battery, external battery, and with the series resistor. Once you feed this resistor, so you can simply get this voltage drops to 0.7. That is the typical supply voltage of the base emitter. So once this is forward bias, and you can have another supply, that is your load side. When a small current goes through this base emitter, a huge current will flow from here, right? So for example, now if you feed 1 milliamps, and if the gain of the transistor is 100, this transistor has a gain of DC gain of 100. Gain is simply IC divided by IV. So you can take 100 milliampere output current from here, right? Just feeding 1 milliamps across the base emitter will allow you to flow 100 milliamps current from collector to emitter. This is the basic principle of operation of a NPN type BJT. And here the PNP type is the opposite. You have to provide negative supply to the base and positive supply to the emitter. And here there's an external circuit is used. Plus goes here, minus goes here. So which always remember this arrow will show you the direction of current, right? So here a small current will flow from emitter to the base. Then it will allow this, once this is biased in this way, a large current to flow from through this emitter to collector. So this current will depend upon the gain of the amplifier, right? Small current, you just give a small signal from the base to emitter through this circuit, and it will allow you to drive large current from this external circuit connected here. So that's the how the PNP type transistor works. So now that's all about the amplifications and all this, what you have learned so far from your first years. Now this was to look at how this BJT works in the power electronics, because we are just using transistors as switches. So in this example, I have used a NPN type transistor to demonstrate. The transistor configuration, you have to provide a base emitter biasing circuit. So there should be this Rn resistor. Its job is to keep this base emitter current to a desired level and this base emitter voltage to a desired level, right? So typically this VN signal comes from your controller. It could be a Arduino, any kind of microcontroller. Typically it's a pulsative, maybe 5 volt to 0 volt signal. You're feeding to here. When it's 5 volt, so the current will go here, and when it is 0 volt, literally it short circuit this supply to the ground. 0 means this potential is at 0 volt, which is virtually grounding this to this point to here, right? That's why it's red disconnected. When you provide 5 volts, there's no connection here like this, the current will flow like that. So your control signal typically 0 to 5 volts, so you have to limit this voltage to 0.7. So you can just calculate what is the required value for R rate. Otherwise, if you just provide this 5 volt directly across the transistor, it will fail. That's why the purpose of having R-in. Any design engineer will select the R-in value based upon the transistor datasheet, as well as the whatever your controller supply voltage comes to this V-in. That is the two parameters you have to consider. And for this your load, load is pretty much pre-given value. So you keep the load here, and you can take the output voltage from here. So input and base are grounded, which means this is typically a cutoff region. So when the switch is off, I'm talking about the switch is off condition. When the switch is off, so the supply voltage simply 0, right? So this is that part of the signal. This is 5 volt and this is 0 volt. I'm talking about when the control signal is at 0 volt, it is literally grounding this point to here. 0 volt means simply this is grounded here. Right. At that point, you know this is 0 volt. Base emitter voltage is less than 0.7. The 0.7 is the typical threshold value of the transistor biasing, as well as the so which means the base emitter junction is reverse biased, no longer is capable to drive current through here. And the base collector junction is also reverse biased, so this is 0 volt. And this is at a positive potential, so this base collector junction is reverse biased. Now the transistor moves to the fully cut off region, which means there's no current here and there's no current flowing here. That leaves, so if the current is I is 0, and the I is 0, so you know like the voltage drop across the resistor is simply VC equals to IR. And current is 0, 0 multiplied by whatever the resistor you have here will give you 0 voltage drop across the RL. So this is 0 volts. So the voltage across the V out is simply VCC minus RL, this voltage. Total voltage minus this VCC minus this voltage will give you the voltage across the V out. As you know, this is voltage is 0. So the full voltage will comes here, right? But the transistor is open. There's no current flowing here. So you can take the output voltage as 5 volt, because this kind of applications are typically for logic gates. But what I'm considering here, when the switch is off, there's no current flow in the RL. So your load is off. If you connect a motor driver, motor controller or something here, the motor. So the motor voltage is simply 0, because there's no current flow in there. That's why, because this circuit is open, the transistor is open, this base voltage is 0. So the transistor now acts as a open in the cutoff region. Right. Now we can move to the saturation. So these are the two conditions of any power electronic circuit. Either transistor is at cutoff region or either transistor is at saturation region. You are not using any other points of the transistor or amplification stages. We are just interested about either the switch is off or switch is on. When the switch is off, it is cut off. When the switch is on, it is in the saturation region. So in order to keep the saturation, this transistor to put into the saturation, you have to keep sufficient voltage across the base emitter. Typically, this should be higher than your threshold value, that is 0.7 volts. So you're selecting whatever the Rin value based on your control signal will satisfy this requirement. So if this is 5 volt and we're selecting whatever the value here for Rin, will provide a voltage or greater than 0.7. So that will enable a small current to flow from base to collector and a large current to flow from collector to the emitter. Same time, the base emitter junction is forward biased, plus and minus, and this junction is also forward biased, high voltage here, and the transistor is fully on, moves to the saturation region, and the maximum current will flow. So the IC current is simply, when it is acting as in the saturation region, so it is literally a closed switch, which means like a piece of wire. There's no any voltage drop. So the voltage drop across this guy is 0 volt in ideal case. VC is 0 volt, and the total VCC goes across this RL. So that is output. This load voltage, if it is a motor is now fully on, right? Motor voltage is simply VCC. But in logic gates, that is a different case. So you take this voltage and it goes to 0. So we are not focusing on that. In a power electronic circuit, remember, if you use a BJT to drive a motor or any relay or any something device, so when you provide your control signal to a higher state, a large current will flow that will enable you to drive this VCC across your load. But in practical scenarios, there's a slightly small voltage drop across here, the switch. That small voltage will lead to a degrade of efficiency. I mean, there's a power loss across the switch. So you have to keep this voltage drop very small. So you have to select it based on your transistor. And so as a power electronic designer, you always like to have the total power supply voltage appearing across your load. Nothing to be go across the transistor. That is a waste of power. So when selecting lowest voltage drop transistors, you can run your system more efficient. Let's take a look at the characteristic of a NPN or PNP type transistor. So this axis shows you the VCE voltage, the voltage across the collector emitter, and this axis is the collector current. Take a look at the cutoff region where we provide 0 volt across here, and the transistor acts as an open switch. So no matter whatever the voltage you provide for VCC, so you can keep increasing this voltage using for example, if your VCC is a battery, like voltage variable power supply, so you can increase this voltage 170 volt here, no matter whatever the voltage you provide in here. So you can keep increasing that, so that voltage will appear across here. So there will be some small leakage current that is in the microvolts or nano ampere range, microamps or nanoamps range. Other than that, that current is very small. Therefore, no matter when you increase this voltage, the output current and the load current will be 0. You can keep this voltage increase to a level until the transistor fails, but we are not interested in that. Remember, in the cutoff region, your collector current is 0, no matter whatever the voltage you apply across the collector emitter. When it comes to the saturation region, you can provide the fully VCC supply, but in power electronics, typically this is your control signal. Could be 5 volts. When you apply 5 volt, and based on your RE in, you can provide a bias current that will lead to drive a large current, and this switch is closed. Ideally, this voltage drop is 0, but there could be slight voltage drop here. Because in ideal scenarios, in order to carry this current through this the load, there should be a small collector emitter saturation voltage. That is this voltage, and this is your collector current, right? So in most of the applications, you can think about your output current. Based on that, you can select your RIN value. In amplifications, we are operating in this region, but for power electronics, we are not interested in this region. We just focus on either transistors cutoff or either it is running in the maximum current, where you can get the lowest VCE drop across the transistor, leading for the more efficient system. The more the voltage drop, this is depending on your transistor data sheet, right? Some transistors, in order to achieve this current, there could be more voltage drop across the VCE, which leads to heat up the transistor, which is sacrificing the efficiency of the system. Therefore, when selecting, you have to get the lowest VCE drop at your saturation region in order to keep the transistor in a cool temperature, as well as to get the highest efficiency. In some applications, we need to take more output current because while using a single transistor is not enough to drive large current across there, because for example, now if this gain of the single transistor is 100 is not enough, you can collect 2 transistors into the Darlington configuration, so which leads to drive more current than the using of a single transistor or connecting them in parallel, right? So sometimes these Darlington transistors, they also comes in 3-pin devices. When you buy from the retail websites, you can pick Darlington transistor if you are interested in more current. So the operation principle is like this. So TR1 transistor, this is TR1. So that is connected to a control signal via this R1 resistor or this Vin. So you provide a control signal, and so that control signal leads to drive a small current across these 2 devices to here, base emitter and base emitter, because these 2 are connected in series. So if you provide 1.4, any voltage greater than 1.4 across this point to this point, so these 2 PN junction are biased. So typically, if you provide 5 volt and selecting any resistor in the range of 100 ohms or something, that will do the job. So that will provide a voltage more than 1.4 volts. So you could see this guy is forward bias and this guy is forward bias, right? So leading this guy forward bias, it will drive a small current across base to collector, because that will lead to drive a large current from collector to the emitter of this transistor. So this large current will flow from here, but it needs to return from the emitter of this the T1 transistor, right? For example, let's say I will drive 1 milliamp current and the gain is 100. So in that case, 100 milliamp will flow from collector to the emitter, right? So your base emitter current is 1 milliamp, so the gain is 100. So 100 milliamps will go from collector to emitter. Now you can see that returning current is the sum of these both base and the collector current. So this is 101 milliamp. So that is again a large current to flow from base to emitter. So if the gain of this transistor is again 100, you can imagine 100 milliampere into 101 milliamps into 100 is your output current, which goes from this collector to emitter. That's a huge current, right? So simply, the gain is the product of two transistors. So the Darlington is there to carry a large current because other than that, the one option is you can use two transistors connected in parallel like this to drive your load, but that only provide the gain twice, but this configuration provide the gain, the product of the gains of two transistors, right? Any questions so far? If you are not understanding anything about this Darlington configuration, you can put into the chat box, so you can turn on your mic and ask.
Sir, excuse me.
Yes.
Sir, do we can use same type of transistors for this configuration? It's mean
typically, yeah.
It's mean we know usually a transistor has a maximum current. It's mean collector currents, no? When we use this kind of configuration, if you want to use TR2 transistor which has more current flow rate than TR1, or if we can use same transistors?
Actually, this TR2 should be capable of handling a large current in the base emitter. Still, you can use the same transistor if it is not exceeding the maximum base to emitter current of this TR2, you can use the same two transistors. But in real world, there are devices in like a package. You don't need to worry about connecting them. You can just buy because it is internally they have designed these two transistors, right?
Okay, sir. Thank you.
Yeah, when you're buying a transistor, you can buy Darlington transistors in the market, so you don't need to worry about designing, because designing will challenging. It takes you time. You have to carefully look into these maximum ratings of the transistors, their heat dissipation and like that. But to make your life easy, the manufacturers have made this configuration in a single unit. So you go to a site like DigiKey or Mouser, you can just type Darlington transistor, so it will come like that. But when you want to design it by yourself, you have to little bit think about the data sheet specifications and maybe try with the simulation software, then you can get your job done.
Thank you, sir.
Okay, you are welcome. Right. So there are some other limitations of BJTs. BJTs are now famous as the MOSFETs and silicon IGBTs. For example, because their popularity is now getting lower, because the gate current should be maintained to turn on the BJT always. That leads to a little bit of complicated, for now the MOSFETs like devices, you just need to provide a voltage signal. But for BJTs, you have to always keep your base emitter current flowing in order to make the switch turn on. right? So that means always you have to this 0.7 voltage drop into your base current can be considered as a waste of power, because your desired is your output load, but controller needs to provide more power in order to turn on the transistor. That's why it's these devices are current control devices. So you need to more power, and your controller needs to feed current driven in order to turn on the device when it is need to be in the on state, right? And the second limitation is they cannot be used for high frequency switching. So the typical switching frequency is 100 kilohertz, ideal for motor controllers, but not ideal for power supplies that comes in small packages. And they have higher switching losses compared to the MOSFET. Switching loss I will explain in a minute. Switching loss is when you switch the transistor turn on and off, not in the steady state. When you turn it on, when it is turning on, in this region there's a power loss, and when you turn it on and then you keep continuing, and this region there's a power loss, that is the conduction loss, and when you turn off again there's a switching loss happening here, right? This during this transition times, turn on and turn off, this loss is considered as a switching loss. That's a significant factor when it comes to high frequency switching, because the power loss is proportional to the frequency. So the transistor's popularity getting down as it has higher switching losses compared to the MOSFETs and IGBTs. The other fact is BJTs have negative temperature coefficient. That is an interesting thing. Let me explain you, just listen carefully, right? Now, let's say I want to, for example, not like a Darlington configuration. Now, I need a motor controller. This is, let's say this is your load. It could be a motor, any kind of power electronic device. So the current is 2 amps, right? You have to provide 2 ampere, but you have one, you can just, rather than like, you assume you have 1 ampere transistor. Each transistor can provide a maximum of 1 amp. So you just planning to connect them in parallel. So it will do the job, because this transistor and this transistor, when it is turned on, they are connected in parallel. So the load current will go from this transistor as well as this transistor. So assuming they equally go return in the emitter, right? So just wait. Okay, so that's the purpose. So you just need to double the load current. So this is your biasing circuit. Either it could be connected to the controller. This is base emitter biasing resistors. Doesn't need to be connected to the supply. It could be connected to your controller. This is your control signal, and this is your load, right? Assume both transistors. This transistor initially you can they even though you buy 2 transistors at the same time, there are some tolerances, right? In that case, assume this transistor, your desired load current is 2 amps. Each transistor can run 1 amps current, but this transistor, maybe due to this manufacturer tolerance, it can drive 1.1 amps, and this transistor then leads to 0.9 ampere, right? Because transistors are not ideal, when manufacturing, there could be tolerances. So at that case, this transistor can drive 1.1 amp, and this transistor can drive leads to 0.9 amps when you connect in them. In simulation, you can get the ideal cases, but in real life, so one can drive more current compared to the other. So when the large this transistor drives current, large current compared to this one, it is heating up pretty easily compared to this one, right? So this current increases and this heat dissipation of the transistor increases, as you know, like the power loss is this current into the voltage across this collector emitter, right? So this guy is heating up faster than this guy. So when this guy is heating up, as you can see, this current is increasing up. It has a negative temperature coefficient. So when the current is going up, it is voltage dropping. So this voltage is dropping, which leads to low resistance, right? Which means like, so it is resistance is going down, which means it leads to more and more current to flow through this guy. I mean, initially it started at 1.1, and when it is heating up, its resistance goes down, which means now this guy's current is going down. So it started at 0.9, this current is going to 0.5, and this guy going to 1.5 amps, and maybe this guy will go to 2 amps, and this guy literally goes to 0 amp. This is really undesirable. So you want to both of them to drive the same current, but due to the tolerance, if one guy is heating up faster, its resistance drops. That will lead to the drive all the current across this transistor, right? Which is not desirable. So you can't parallel the BJTs because of their negative temperature coefficient. But for the MOSFET, you can connect them in parallel. I will explain it in the MOSFET case. So assume you have two MOSFETs. So MOSFET is acting as a completely different compared to the BJTs. So if this guy is driving large current, let's say 1.1 amp, and this guy is 0.9 amps. So this guy is heating up faster, is RDS on. This resistance increases, which means when the resistance increases, this current will again naturally drops to 1 amp, and this guy current will increase to 1 amp. So it will come to a thermal equilibrium to a level the both devices share the same current, not like in BJTs. The MOSFETs, because due to their positive temperature coefficient, if one transistor MOSFET drives a large current, it is heating up faster and its resistance increases, which means it is reducing the current again back to a normal level and share the current into the same level. But in the BJTs, due to this negative coefficient, so if one guy start a large current, so most of the current will go through this guy, and this guy literally do nothing, just staying here and doesn't do any job. So that is really undesirable when you parallel transistors. Is that clear? I hope that is clear for everyone. If you have any questions, you can ask. And the other one is, I'm not going to cover more details about, like BJTs has secondary breakdown limit, because if one guy goes to higher temperature, so inside there could be some hot spot. So that will lead to fail of the transistor. Just read these references, you will understand it. So that is not necessarily required for this course at your level. But just remember, these are the primary limitations. First limitation is you have to provide constant current always to turn on the device. So your controller power consumption is large. For example, now if you take an Arduino to drive your controller, so if your Arduino is run with the battery, so you might within 1 week you have to change this battery because there's a huge power loss in your controller. If you use a MOSFET, you can maybe for 1 month, you can use the same battery for your Arduino because the MOSFETs are just voltage-driven devices. It doesn't need to drive any current, right? So more efficient when you're using MOSFET compared to the BJTs. BJTs require current, so it leads to low efficiency. And they can't run in high frequency. Typical frequency is less than 100 kilohertz. Higher switching losses when they turn on and turn off, there are losses that is higher compared to the MOSFETs, and they can't be connected in parallel due to their negative temperature coefficients. You can see when the current is increasing, the voltage drops. The slope is the resistance. So you can see the resistance is V divided by I, right? So when the current is increasing, the resistance drops, which means it will go to one transistor to carry all the current. So now we are moving to the MOSFETs, and I will play this video so you can get some clarification about how this MOSFETs works. Right, MOSFETs are the ideal candidate for many power electronic applications.
Have you ever wondered what makes MOSFETs different from other transistors? Today we explore the internal world of MOSFETs, or metal oxide semiconductor field effect transistors, and we'll discover how they operate and how they differ from current-driven transistors in design and function. For this tutorial, we'll focus on the N-channel MOSFET. Much like its predecessor, the bipolar NPN junction transistor, N-channel MOSFETs use N-type and P-type material to form semiconductive paths along with an additional metal oxide layer. For terminology, the BJT emitter terminal becomes the source terminal in the MOSFET, the base becomes the gate terminal, and the collector becomes the drain. But what are P-type and N-type regions made from? Pure semiconductor materials like silicon are relatively good insulators because their electrons are tightly bound and are not free to move around. By adding impurities through a process called doping, P-type and N-type regions are created. These regions either have too many or not enough electrons, resulting in looser bonds between the atoms. N-type or negatively charged regions are doped with atoms such as phosphorus that have more electrons than silicon atoms. When the atoms bind together, the extra electrons are free to move and are attracted to positively charged regions. P-type or positively charged regions are doped with atoms that have fewer electrons than the silicon atoms. When the atoms bind together, holes are created due to the deficit in electrons. Holes are also free to move, but they are attracted to negatively charged regions. MOSFETs use a few additional elements to transform the P-type region between the N-type source and drain regions into a conduction channel when voltage is applied to the gate. A layer of metal oxide placed between the gate and the body substrate, along with an additional connection between the source and body, forms a small capacitor-like structure in the conduction channel. This is the metal oxide part in the term MOSFET. Applying voltage to the gate allows current to flow through the capacitor, which begins to charge and generate an electric field. This is the field effect part of the MOSFET term. Electrons gather at the oxide layer, filling in the gap between the source and drain. This is referred to as the conductive region. When enough electrons have gathered to create a path, current flows in the conductive region and the MOSFET starts to turn on. The conductive region has a small amount of resistance when the MOSFET first turns on. As the capacitor charges, the electron field becomes more crowded. With added conductive paths to follow, the resistance decreases until the MOSFET is fully on. MOSFETs have other characteristics that emerge from the union of P-type and N-type materials. Whenever an N-type material is joined to a P-type material, a diode is formed. With two N-type regions and only one P-type region, the N-channel MOSFETs have two diodes formed that are connected anode to anode. However, the diode connected to the source is shorted out by the source body connection discussed earlier, and therefore has no effect on the operation of the MOSFET. The remaining diode connecting to the drain of the body allows reverse current to flow uncontrolled from the source to the drain, whether the MOSFET is on or off. Additional external components are needed if current is to be blocked in both directions when the MOSFET is off. For basic operation, if voltage at the gate is higher than the source voltage, the N-channel MOSFET is in the on state. P-channel MOSFETs work in much the same way, but the N-type and P-type materials in switched locations. If voltage at the gate is higher than the source voltage, the P-channel MOSFET is in the off state. Now you understand the basic operation of MOSFETs, how they can be broken down into the materials used, and how those materials interact.
Okay, so you might get an idea about the construction of MOSFETs. Remember this, the MOSFETs, they have this kind of body diodes, right? This is not someone has put in there. This is the body diode comes naturally because of the construction of the MOSFET, right? It is not put someone by purpose inside the MOSFET. It is a natural phenomena happens when you build this NPN type this PJ MOSFETs. This body diode comes naturally inside the transistor. It's not someone has put it externally, right? So it's due to this construction. So the metal oxides, we are just covering the metal oxide semiconductor field effect transistors, also known as MOSFETs. So they are 3-terminal devices like transistors, has a gate, drain, and source. So let's take this example, N-type MOSFET. You have the gate here and source here and the drain here, right? So the gate source is your the controller, which is normally connected to your controller. So this is voltage driven. So whatever the voltage that you provide here, doesn't need to have a control resistor always, right? So there's no purpose of using a control because you don't need to control any current through this device. It's just voltage driven. There's a other interesting thing is there are some capacitances across these all three devices, parasitic capacitances. So that is you have to consider when you're dealing with the high frequency drivers. Most of the time for your level, you don't need to worry about, but when it comes for design engineers level, these values should be taken into account in your design. For my designs, what I have done in all last years, I have always worried about these values because that is troublesome in some applications, right? So there are two types of MOSFETs in the market. The first one is depletion type. So like, you know, in PLCs, you have normally on and normally closed switches. Now the depletion type, this is a depletion type. The symbol is different. Like in depletion type, you can see this gate that is a continuous line, right? In the enhancement type, this is a broken, it's a segmented line. See here, segments. And this is how you just identify depletion type and enhancement. Depletion is just a straight line. So in using circuit symbols also, you just make sure whether you're using a depletion or enhancement type. The difference is in the depletion type, the transistor requires, I'm talking here, a gate voltage to switch the device off, which means it is naturally, if there's a no signal, the transistor is on, right? It is switch on. So providing a gate signal, you can turn off the device. It is like a normally open, normally closed switch. But in enhancement type, it's completely opposite. This is the wide use, like when you provide a positive voltage here, your device is turned on, which means this is a normally open device. When you provide 0 volt, your device turned on. That's the two different. Normally, it either if you select depletion, it's a normally closed switch. If you use the enhancement type, it's a normally open device. So there is an additional terminal code substrate, so which is connected here. It is not always used, but it is internally grounded. It could be grounded too, but typically it doesn't matter in many applications. So, in BJTs, we have learned the current in NPN type BJT, the current can flow from collector to emitter, right? There's no current flow in the opposite direction. Interestingly, MOSFETs can drive current in both directions. If you provide a control signal of 5 volts, you can drive a current through here, right? And how to drive the current in the opposite direction? That is because you have a body diode here, right? That is uncontrolled, because if you give a positive voltage here and negative voltage here, and the current can flow through your body diode, right? That is uncontrolled. You can't control that current. Remember, like, it's not a unidirectional, it's a bidirectional device. From this, from using the gate signal, you can control the current in this direction, but you can't control any current that comes from this side, right? The voltages is like this. The N type, the most common one. So you have to provide gate source voltage, this voltage, a positive voltage to turn on the device. And when this voltage is 0, the device is turned off. If you provide a negative voltage also, that is less than 0, that the device is turned off. For the P type, so setting a positive voltage across the gate and source will these two devices to turn off, and 0 volts also leading to off. But if you provide a negative voltage across gate to source, the device can turn off. So always you need to have negative voltages to limit when it comes for P-channel MOSFETs. Right. So this is N-channel type MOSFET example. Now this is a cutoff characteristics. So your control signal is now at 0 volt. So which is literally connecting to the ground, and there's no current will flow through the device. The device is turned off. Your load doesn't have any voltage. All the voltage come across the switch. No power across the load. And the other region is the saturation. So you have to provide the voltage whatever to or greater than your threshold voltage. The threshold voltage is the minimum voltage that requires to turn on the MOSFET that is available in the data sheet. So if you provide this voltage more than your threshold, so the device turn on, so it does a virtually short circuit, but there's a voltage drop that is based on the internal RDS on resistance. This current into RDS on is the voltage drop across the device. Right. That is, I think, pretty simple to understand any electronics student. For P-channel MOSFETs, this is completely different compared to that. So they are also known as high side switches. And when it comes to edge bridges and devices, sometimes you have to connect your load. Connect one side of the load should be connected to the ground. In the previous example, you have seen like one side of the load is connected to the positive and other side connects to the ground. In most of some applications, you need to have your load is grounded. That is really helpful in some application. If you want to find the voltage across the resistor, you can just get using a resistor divider and find out this voltage. Yeah. So in application where one side is grounded, one side of the load is grounded, you have to go with the high side switches like P MOSFET. Now here, take this example. When you turn this gate to the ground, right? So you know this voltage is 0 volt, and this is plus VDD. So VGS is the gate voltage with respect to the source. By looking from source, assuming like a source is your reference point, this guy has a negative VDD, right? Because with respect to the gate, this voltage is VDD. With respect to the source, this voltage is minus VDD. That is VGS. VGS is minus VDD, which is higher than the threshold level, because in P MOSFETs, the threshold voltage is negative. And this voltage is higher than the threshold, the device is turned on. That means like when you put this switch to the 0, the PMOS is turned on, so the current will flow through this MOSFET to the load, and the load is driven. Now, when you connect this switch to the off state, which is you connect the ground to the VDD, and gate voltage is VDD and source voltage is VDD. VGS is the gate voltage with respect to the S source, which means when they are in the same voltage, the voltage difference is 0, the VGS is 0, which means that is lower than the amplitude is lower than the amplitude of the threshold voltage. The device is turned off. It is moved to the cutoff region. So that is how you can turn on and off P MOSFET. So now you can understand it cannot be directly driven by a typical Arduino microcontroller type. In most cases, you need to have external gate drivers. Any questions so far? If you move into the characteristics. Okay, now we move into the characteristics of the MOSFET. As you know, MOSFET has, in power electronics, we either operate the MOSFET in cutoff region or in saturation region. The linear region is typically used, is also used in biasing the MOSFET. Right, in the cutoff region, VGS is less than the threshold voltage of the MOSFET. So, which means the transistor is at cutoff. That means that there's no current flowing from drain to source. So ID is 0. In the linear region, where VDS is less than the VGS minus threshold, the transistor is acting in the constant resistance region and behaves like a voltage control resistance. That is in this either in these points of the transistor, which we can consider it is as the in the linear region, ohmic region. Most of the time, any design engineer would like to keep the MOSFET to a lowest VDS drop as well as the highest maximum current. So this is the desirable points where you can get the maximum current as to a level of the lowest voltage drop across the MOSFET. Okay, and the saturation region is where you will get you have the constant drain current while you can increase the VDS on, but that is not interested. But in most power electronic applications, you can either operate your device in the cutoff region or in the close to this linear region where the it is in the ohmic region. Simply the resistance RDS on into the output current will determine the voltage drop across the drain to source. The other interesting device in power electronics is the IGBTs. So the IGBTs are combinations of MOSFETs and BJT transistors. So sharing the interesting features of both devices. Now, IGBT stands for insulated gate bipolar transistor. As I mentioned, it's a mix of conventional BJTs and MOSFETs. So it is three-terminal devices. It has a gate and collector and emitter, not like drain and source compared to the MOSFET, and gate, collector, and emitter. And so IGBTs are controlled by gate voltage, not like the gate current of a transistor, right? This is a typical arrangement. You have a N type of channel MOSFET here, so which means you can drive it as a voltage signal. So when your controller provides a voltage signal, the controller provides a voltage signal. So this gate source junction of this MOSFET is turned on, so which drives a current here. So that current will turn on this collector, the base collector of this PNP transistor. Actually, this should be emitter inside, right? So that leads to drive a current, so enabling a large current to flow through this transistor. So if you just use the transistor, you have to keep a continuous current from your controller, but that is it has been get rid of by using this MOSFET. So you just need to take a voltage control signal here. So it will drive a current, large current from the output side. So the circuit symbol of a IGBT is similar to a BJT, but the difference is you have extra straight line type character in here, right? So emitter current is same as the collector current. So you just need to provide the voltage signal, not like a current signal. So they can come with different packages. This is a simple example of our semiconductor TO252 type package type IGBT, and it could the maximum voltage that can stand is 650 across the collector and emitter. This is the maximum voltage, and 16 amperes is the maximum current that it can flow through the transistor. And if you want a bigger large power device, so you can go with this kind of ABB. These kind of devices are used in power grids, so that can withstand for higher voltage at the collector emitter and driving large currents. Okay, so that concludes the operation of a IGBT. You just need to know is a voltage-driven device, and however, not compared to the IGBT MOSFETs. So this on resistance is very much low in IGBTs. So equivalent MOSFET compared to equivalent MOSFET, the RDS on is very low in IGBTs. So they are typically used in inverters, converters, and power supplies. Right. So this is taken from a data sheet. This is the symbol of IGBT. Sometimes, you know, there are 4 devices in IGBTs, not like 3-pin devices. Additional emitter is provided as number 3 for gate driving purposes. So when you provide 7 volt plus any voltage lower than 7 volt, the device is turned off. So when you're providing any voltage over than that, so device is turned on. So anyone has any idea why rather than having this pin here, so they have used pin number 3 as well here? Why they are using 2 pins? Why they can't use just single 3-pin device? If anyone knows the answer, just type on the chat box. I'm just asking why it is. What is the purpose of having 4 pins compared to just having this pin? What is the purpose of this? Okay, that is I'll let you to figure it out, right? Just go and look into that is, as I mentioned, so driving the IGBT is not like easy, so you can't just drive it from Arduino. So you have to have a gate driver, gate drive. So for the gate drivers, sometimes it is desirable to have direct pin across the emitter rather than using this one. So this one is used for power driving, and this one is used for gate drive, right? This is your power circuit and this is your control circuit. So for control circuit, this pin is used, and for the power, so this pin is used. And so if you use the same pin for the gate driver, so any small resistance across this pin, like maybe 1 milliohm or something. So if there's 100 ampere goes, there is a voltage drop in this pin, right? So your gate signal needs to compensate that voltage drop. 1 milliampere into 0 is 100 millivolts. So let's say like the threshold voltage is 3 volts. So you have to provide the voltage signal 3.1 volt, because you have to overcome this 1 millivolt drop in this pin, right? But if you use directly across here, this voltage drop is down, right? You can just use 3 volt driving signal. So IGBTs are used in motor drivers as well as in induction heaters. Now in this example is a 3-phase motor driver, which is driven by AC input. So the AC voltage is rectified to a DC, and this rectified DC voltage is then inverted to a 3-phase supply using IGBTs. And for induction heaters, so again, it is driven by AC supply that is rectified, and this is a resonance. Typically, a load could be connected to resonant converter or half bridge. So when the IGBT is on, the current will flow here. When this IGBT is on, the current will flow here, it's providing a sine wave across the load. Now we can compare the BJTs, MOSFETs, and IGBTs in this table. So the driving signal or the control signal of BJT is based on current signal. So you have to keep continuous current to turn on the device. The MOSFETs and IGBTs just need a voltage signal. So it is more efficient, these devices compared to the BJTs. So the output current capabilities of BJT is less than 500 amps, and the MOSFET is lower than 200, but IGBTs can drive currents over than 500 amps. Switching speed is low in BJTs, and the MOSFETs is limited to 10 kilohertz to 300. but IGBTs can, the MOSFET, the only advantage is MOSFET is it can drive high frequency, but IGBT switching frequencies are limited to maybe maximum 20 kilohertz according to this reference. So the IGBT cost is really high compared to MOSFETs and BJTs, right? So some applications, it just require a MOSFET, or sometimes if you cost is not enough, you are not worrying about the cost, you can go with IGBTs. But in most cases, MOSFETs are preferred because it can drive, it can operate in high frequency, and the load current is not a big deal. Nowadays, blooming up with the silicon carbide MOSFETs. So compared to silicon MOSFETs, the silicon carbide MOSFETs is superior, and it is filling the gap between IGBTs and typical silicon type MOSFETs. So it's a new technology, and they have the wide bandgap material. So the applications of silicon carbide MOSFETs are power factor corrections circuits in solar inverters, DC to DC converters in electrical vehicles and hybrid electrical vehicles. Now, in this graph shows the frequency, switching frequency. You can see from silicon devices, silicon MOSFETs, they can go up to around like 300 kilohertz of switching frequency. And they are, due to their power capability, it can drive for the power ratings maybe 30 kilowatts, right? But for the IGBTs, their power rating is much higher compared to the silicon MOSFETs, but their switching frequency is lower than the silicon MOSFETs, right? IGBT has high power, but the switching frequency is low. The silicon MOSFETs have higher switching frequency, their power consumption is low. But for silicon carbide, they have the same power rating as IGBTs, but the switching frequency is also higher than to MOSFET, so making it more suitable for new power converters. But the silicon carbide MOSFETs are more expensive than either silicon MOSFETs and IGBTs. Now this video will show you silicon carbide and silicon and gallium nitride technology. That gallium nitride is a new technology that is used for coming as a replacement for MOSFETs.
The secret of your success lies in the power of choice. Silicon, silicon carbide, and gallium nitride power semiconductors come with very unique characteristics, offering different benefits. To provide the highest level of system performance in your application, you have to know what each of these technologies can bring to your designs. Silicon, silicon carbide, and gallium nitride, when to use them. Gallium nitride is a technology of choice at fast switching frequencies, providing the highest efficiency and power density at an overall optimized system cost for power-hungry applications. Wide bandgap materials complement silicon solutions, pushing the envelope of power efficiency, size, and weight reduction further for even higher levels of performance and enabling new topologies. Silicon carbide can withstand high temperatures and harsh environments. In addition, the possibility to use standard drivers with it makes silicon carbide an easy-to-use option for improved performance compared to silicon. Choosing legacy silicon provides you with the best price-performance ratio. This mature technology addresses a large variety of use cases in which price performance is desired. We know that the choice is not easy, but as your trusted partner with our several decades of experience in power semiconductors, Infineon, the expert in all three power technologies, is there to help you. We are also a committed and well-positioned supplier to fully support your growth at the highest quality standards. Our ramp-up capability, as well as 300-millimeter wafer fab for power semiconductors and continuous R&D investments in next-generation wide bandgap and silicon technologies, together with our technology know-how, is all there for your success. Choose from our broad power portfolio of high-quality, highly efficient, and ease-of-use products. Visit our website to learn more about wide bandgap technologies.
So the Infineon is not only the manufacturer who supply silicon carbide MOSFETs. There are some other manufacturers like Cree, CREEE. This company also manufacturing silicon carbide MOSFETs. I have used one silicon carbide MOSFET from Cree for one of the power supply project I did last year. So the cost of a MOSFET is around like $20 compared to a MOSFET. So the MOSFET price is around $7. So the silicon carbide devices are more expensive compared to the typical MOSFETs, but they have superior characteristics for our application because we had to deal with the voltage over around 1,200 volts and current up to 35 amperes. So that's why we went with silicon carbide devices rather than using just silicon. Right, so it's all depending upon your application. So there are a wide variety of options available. Either you can go IGBT, silicon, or now either gallium nitride. So it is the role of the design engineer to select the right devices based on the requirement of your manufacturing. Right, so this is again a comparison of silicon carbide MOSFETs versus IGBTs. So the IGBTs were there. Now it is simply replaced by silicon carbide MOSFETs. So all of them are using power electronics. So the both IGBTs and MOSFET are voltage driven, not like the BJTs. The BJTs require current, but IGBTs and MOSFETs just require a voltage signal. Due to the bipolar nature of IGBTs, they carry a large amount of current, which is with a low saturation voltage, resulting in low conduction losses, and they can be used in high power applications. Silicon MOSFETs have low conduction losses as well as, but depending on the device drain to source on resistance, right? And silicon MOSFETs are used in high frequency applications. They have the operating frequencies higher than IGBTs, where the high efficiency is the key. Silicon MOSFETs carry less current than IGBTs because IGBTs can drive more power, like I showed you in the graph. Now the silicon carbide MOSFET, silicon carbide are similar to silicon MOSFET with respect to the device type, but the silicon carbides use wide bandgap material that allows to operate in the same high power level as the IGBT. The power level is same as IGBT while being able to switch at high frequency. IGBTs are limited to low frequency, but silicon carbide can drive high frequency like silicon MOSFETs and can handle more power like IGBT. So these are the three symbols of MOSFETs: silicon carbide MOSFETs and IGBTs. The circuit symbol of silicon carbide is same as the silicon MOSFET. IGBT is a little bit different. So the voltage range of silicon MOSFETs are lower. You can see its maximum voltage rating is 650. IGBTs can have slightly voltages higher than that. Silicon carbides also can drive voltages more than 650. Switching frequency is silicon carbide is higher than IGBT and typical silicon MOSFETs. The operating voltage, the gate voltage is 0 to 15 positive for MOSFETs. IGBTs can drive from negative voltages to positive voltages. So either, in order to turn off the IGBT, you can provide 0 volt, or either a negative voltage will turn off the device. Silicon carbide, but this negative voltage should be higher than that is for the designers of the gate driver. But silicon carbide just need a very low negative value. You can still turn off the device, but if you want to turn it in a faster rate, you can use negative voltages. 0 voltage will also turn off the device, but it takes some time, right? That's why you apply negative voltage to turn off rather than just using 0 volts. The power level of silicon carbide is higher than IGBTs. The applications are like this. Right, now it's time to work on a simple application. You need to understand the typical parameters. So you can use this MOSFET, and so data sheet is given. I will copy in the link. I will show you the data sheet of this one. So I have put the data sheet on the chat box so everyone can download that, and also the circuit for this circuit model here. So both files are in the chat box now. So all you need to do is just simple activity. I will explain the data sheet first. So now all you need to do is we will change this. This is a N-type MOSFET, and we have a load, and we are going to measure the load current and voltage drop across the MOSFET. And this is our gate drive voltage, and this is our power voltage that applies to the load. So all you need to do is change this DC voltage across this MOSFET, starting from 2.5 to 10 volts, and simulate and observe this VDS voltage, IDS current, and the power dissipation across the MOSFET. Power dissipation of the MOSFET is simply this current into this voltage, and power of the load, should be this current I squared R into I squared R, this current squared into this resistance. And if overall efficiency is the ratio of input power to the power that should be on the load, right? This is the power loss across the device. So lower the power heat dissipation across the MOSFET, the higher the efficiency. You can just compare the efficiency of the system. Just this is your input power. Either you can use an ammeter, and this is the same current into this is your input power is this voltage into this current. Your output power is I squared R here. So some part of the power is dissipated across the MOSFET. You can just calculate these parameters. These are the steady state operation. So in the file that I have sent, just there's a voltage source. Just replace it with this battery voltage using a battery, and you can try to fill this. But I will explain you the how to read the datasheet parameters of this one first. Okay, this is our MOSFET. So I will start from here. So BVDDS is the breakdown voltage. That is the maximum voltage you can apply across the drain to source. RDS on is the on resistance. That is to 9.5 milliohms when the device is fully on. Its internal resistance is 9.5 milliohm. Package is TO 2220 220 AB type package, true hole one, not surface mount. So it can drive 98 of ampere current when it is internal junction temperature is at 25 ampere, right? So typical applications are motor control, DC to DC converters. Right. So the maximum ratings, these are the absolute maximum ratings. So if you exceed any voltage beyond that, the device will fail. So the VDDS voltage should be limited to 100 volts, and your control signal to drive the gate voltage signal should be within -20 to +20. And the continuous drain current that you should flow through the device when the device internal temperature is at 25 Celsius degrees junction temperature, you can drive 98 of amps. But when it is heating, so if the junction temperature becomes 100 degrees, you can drive 62 amps. Otherwise, the device will fail. So it can drive some pulsative. The body diode can drive 90 amperes of current, and pulsative current can lead to 92 amps. These are the thermal characteristics. The maximum power dissipation is 2 watts. And this is the really important thing. So the gate threshold voltage, so the voltage you should apply to turn on the device is typically 1.9 volts. So your control signal should be more than 1.9 volts in order to turn on the device. This is a threshold voltage, right? If your voltage is either less than 1.4, this is the minimum value, the device is off. So the static drain on resistance RDS on could be within these values based on your gate drive signal. If you drive more, if your gate signal has a high voltage like 10 volts, so you can get a lower RDS on. So the body diode forward voltage is typically 0.8 volts. So the capacitances, like I showed you, there are some parasitic capacitances inside the MOSFET. Their values are there. It is not required for your undergraduate level, but when it comes for design engineers level, so when you're doing PhDs, so you have to deal with these capacitances, especially when you use gate drives to drive this MOSFETs. Turn on delay time is, even though when you apply a step response type control signal, it takes certain time to turn on the device. These parameters are shown here. Right, these are the output characteristics of your drain voltage here. So if you apply a small voltage like 3 volts, you can just get the device turned on. So any voltage below than 1.4 will turn off the device. That is in the cutoff region. So applying higher and higher gate voltages, you can drive the device into higher current ratings. So I hope this will explain the data sheet. Now all you need to do is go to the exercise and move it to here and fill this table by using the simulation model. Can everyone see the screen now? And can you work on this one now? Any questions? Anyone has any clarifications, you can ask now. Anyone got the value for VDS when it is 2.5 volts? Can put on the chat box. Okay, I will let you to work on this one leisurely. Looks like you guys are not like active learners. I have understand that really well. So it's up to you. You will do your thing, and this is the second one. Here we can apply a gate drive signal here, and these are the frequencies you have to change. Based on that, you have to measure the rise time, fall time, and conduction loss, and the switching loss, right? Let me show you this. How should I do this? All right. So this is the previous table. We had the continuous response and power losses. Now this is a dynamic response. So this is your gate drive signal. I have used it as a square wave. You can see this is turn on period and this is turn off period. The turn on period is 50 microseconds and turn off period is 50 microseconds. And this in order to start from 0 to this turn on voltage is 10 volts, turn off voltage is 0 volts, right? This 100 nanosecond is from starting from 0 to 10 volts. The time it takes to reach to 0 to 10 volts is around like 100 nanoseconds, which is very small compared to this one. This is the falling edge time delay. And again, I have put 2 delays for this period as well. So basically, this is your control signal that these typically comes from a gate drive. Then I will go to analysis, transient, and simulate for 300 microseconds. Then I can get this kind of waveform. Right, so I will reuse separate curves. Now you can see when my gate signal is at 10 volts, so the device is turned on. So IDS current will reach to nearly 10 ampere because this voltage is 50 and this resistance is 5. So my current is the drain current is 9.99 ampere. And VDS is this voltage drop across the device. You can see when it is turned off, this voltage is nearly 0. 60.46 millivolts voltage drop at 10 ampere. So you can calculate the power dissipation across the MOSFET. What I want to show you is dynamic losses. Dynamic losses are, so you have to just zoom it out. Right, I will zoom this one a bit. Right, this is how you're gonna find the turn on losses of the MOSFET, right? So you can see your gate signal is from starting from here, it takes 100 nanoseconds to reach to the 10 volts, right? So your gate drain current reaches here and the voltage drops here. So during this time, there's a power loss. There's a power loss in this region. Okay, so how to get this power loss is simply, so you have to take the average of this average current here. Consider this region. Take this region, take this time period. I can put my cursor here, another cursor here. Right, so now this is the turn on time of a transistor. So it takes around 20.32 nanoseconds. So during this time, you can see the voltage takes some time to drops to 0, right? And the current takes some time to reach to there. So there's an overlap. I mean, it is not just jumping straight forward. So you can see during this period, there could be an average voltage. Average voltage is this voltage divided by this voltage. So that is the average voltage appearing this time. And this is the average current appearing this time. So this value plus this turn off current divided by 2 will give you the average current. And the average voltage is this voltage plus this of voltage divided by this. So that half, right? So you can find the average voltage and you can find the average current, multiply by them will gives you the average power dissipation during this period. So that is the power, but actually the energy consumption is, so you have to multiply it by this time duration 20.32 seconds. Okay, now in this example, let me find out what are the values. Okay, I will just find the average current. So you can see here the B is 9.56 and the this current is A at 9.85. Nearly it is 9.56 divided by 2 is your average current, right? And so average voltage, you have to go here, and that is typically should be 5 volts. See, this is 25, 50 plus this value divided by 2, nearly 25. So that is the power, but so the energy consumed during this period is this like this average current is 5 ampere. This average voltage is 25 volts. So into this time duration is nearly 20 nanoseconds. That is your energy dissipation at non time, right? Convert into the seconds, then otherwise you can't get the. So T on is during this transition, the energy loss, right? So the same thing should be applied to find out the power loss during a turn off period. So you have to zoom this out, and you could see here when it is turning off, there's an overlap. The current is not suddenly drops to 0, so it takes some time, right? So this time duration is around 22.17 nanosecond. So the turn off time should be again calculated. The energy loss at T off. So this average current into this same values into 20.2 nanoseconds. So now you know the right. So that is the power dissipation in here. So we know the power dissipation here. This is that value. sorry, the energy dissipation here, and energy dissipation of the MOSFET in here. That is this one, and this is this one. So we know both values, right? So in order to get the dynamic losses, the switching losses, that is simply, so you have to ET on plus ET off. So that will give you the both power energy dissipation. So this is for this time duration, total time duration. That is 1 upon the frequency. So our frequency was, we know this time period is, according to this VG1, it was around 100 microseconds, as I could remember. So that will give you the dynamic losses. So the more the higher the frequency, you have more losses, and it is the device is heating up faster. So the total loss of the MOSFET is this dynamic losses plus this static loss. Static loss is when you have driving this current, that power is simply this current is 10 amp into this voltage drop, what you got from there, this voltage drop here across here, maybe very low value, 65 millivolts or something. So the total power dissipation is this one dynamic loss into the static loss. So you have to know these values when you put your heat sink, and how to find the right appropriate heat sink for this device, or use the right package. If you have questions, you can ask, because I'm not no longer talking the simulation anymore from this point. If you have clarifications, it is time to ask them now. Right. Hope everyone got the chance to see this, and I'm moving to the next section. Okay, so now you can fill this the rise time, fall time, conduction losses, and the switching losses in this table for different frequencies. So you will understand that more the switching frequency, so you have to change this frequency. So it is 50 microsecond turn on and 50 microsecond turn off, means total time duration is 100 microseconds. So the frequency 100 microsecond, simply 10 kilohertz. By using, you can increase the frequency to different values and see what will happen to your switching loss and dynamic loss. Conduction loss will be the same, but the switching loss will increase with the frequency. Okay, now I will show you application of a silicon carbide.
All electric vehicles need to be charged. With the growing market of electric vehicles, the industry has put forward more requirements for the performance of charging piles. Luckily, the emergence of 1200-volt cool SiC MOSFETs has improved the charging pile industry to make the charger smaller, faster, and more efficient. Let's start by seeing Infineon's power solution positioning for EV charger today. As you can see, 1200-volt cool SiC MOSFET discrete solutions are suitable for almost all power ranges. So why are electric vehicle charger applications quickly adopting 1200-volt silicon carbide MOSFETs? One of the main reasons is topology simplification, both in AC-DC stage and DC-DC stage. In DC-DC stage, there has been a move from two cascaded interleaved LLC topologies that use 650-volt silicon components to the implementation of single full-bridge LLC solutions. With a 1200-volt SiC MOSFET DC-DC in a full-bridge LLC topology, part count is reduced by 50%, thus enabling two inverter stages with the same footprint. We can also simplify the design effort by using a simple topology. An example of this is that a 4-piece 1200-volt silicon carbide cool SiC MOSFETs can replace the 8-piece 650-volt silicon MOSFETs. In AC-DC stage, it is the same. By using silicon carbide MOSFETs, a 3-level topology can be replaced by a 2-level topology, which translates into higher efficiency with just half of the number of devices. Finally, this makes it easier to fulfill requirements on fast charging cycles by increasing output power and high power density. Ultimately, with the change of technology, there is also a reduction of engineering costs. Cool SiC MOSFETs are less temperature dependent than silicon MOSFETs. Even with the same drain source on resistance, the conducting loss will decrease due to the voltage drop reduced at working temperature. The 1200-volt cool SiC MOSFET also has a smaller output capacitance, POS. This means that less discharge time is needed during the transient period when the current changes from the MOSFET to the diode. Therefore, we can set a smaller dead time to get a smaller diode conducting loss during the transient period. So, by using 1200-volt cool SiC MOSFETs, we definitely achieve a loss reduction. Let's now go through the key advantages of silicon carbide MOSFETs in a bidirectional charger. Unlike the IGBT that needs to integrate an extra full-rated diode, cool SiC MOSFETs can conduct reversely with full power. In the graphic, you can see the body diode with positive gate voltage, where the forward voltage is much lower than the one that is not gated. Therefore, synchronous rectification can be used on the reverse conducting quadrant to overcome higher forward voltage of the body diode and get less conducting losses without extra diodes in parallel. Based on a use case example of a 30 kilowatt EV charger, silicon carbide-based semiconductors can have a higher conversion efficiency due to a 50% components reduction and power increase, as well as to its modular designs, which upgrade system power and voltage levels on demand. Also, they allow reducing the size and weight of the charging stations, increasing the ratio of resources used per kilowatt installed. Finally, they simplify the topology in order to reduce the design effort. Hopefully this video was interesting and provided you some hints on 1200-volt cool SiC MOSFETs in an EV charging application.
Right, so the silicon carbide devices will lead to more efficiency, as well as it will reduce the size of the power converters. For example, because now using a silicon carbide, so you can drive frequencies more than 300 kilohertz, so which will place for very small size capacitors and small size inductors in your design, right? So if you have lower frequencies, so you need to have like a bigger capacitors and bigger inductors, so that will make the design bulky. So that's why due to these new technologies, so the power electronic devices are getting smaller and smaller and more efficient. Let me show you another example. Can you see the video?
Are you still using an IGBT? Perhaps you haven't heard about the cutting-edge Cree MOSFET technology. If you're ready to take still using an IGBT, perhaps you haven't heard about the cutting-edge Cree MOSFET technology. If you're ready to take your power converter designs to the next level, it's time to say no to the IGBT and yes to the Cree MOSFET. Cree has made major advances in MOSFET technology that have totally changed the power conversion game and opened up some exciting design options. So let's get technical. Traditional MOSFETs are great because they have low switching losses, but they can't handle higher voltages, above 800 volts or so. IGBTs can handle higher voltages, but they have high switching losses. Cree's MOSFET technology marries the best of MOSFETs with some cutting-edge Cree technology that work at voltages up to 1700 volts with low switching losses. The result is that the Cree MOSFET can replace the latest generation IGBTs, but with 6 times lower switching losses. Need proof? Take a look at these two identical Cree evaluation kits. They are both configured to run as boost converters, switching at 100 kilohertz. Look at how fast the IGBT is heating up. That's the result of the 6 times higher switching losses in the IGBT. And high IGBT switching losses mean that you need to reduce the switching frequencies, which results in larger parts, like inductors and capacitors. And larger parts mean a lot of extra money. Not convinced? Let's see an example application. Here's a 10 kilowatt power converter built with a Cree MOSFET. And here's one built with an IGBT. Did you spot the difference? So to recap, an IGBT has 6 times higher switching losses than the Cree MOSFET. This requires designers to switch them slower or use more of them. Both options are costly and produce larger systems. With the Cree MOSFET, you pay a bit more for the actual MOSFET, but you save a lot of money at the system level. The end result is a product that is cooler, smaller, and better. Remember, just say no to the old IGBT and say yes to the Cree MOSFET. Don't believe us? Then order your Cree MOSFET evaluation kit and compare us to your favorite IGBT yourself. The new way to design your high-power products is by using Cree's high-frequency, high-voltage MOSFET. Start revolutionizing your designs today.
Okay, that is the end of this lecture. And so these are the more readings. So if you're interested, go and see the how to use a select appropriate gate driver for your MOSFET drives and power MOSFET selecting design guides for Toshiba and silicon power devices modules application notes from ARM semiconductors. So if you need interested in more learning, so it's better to read these things. So that will wind up this lecture, and I will recommend you to use your time to work on the simulation in this time, right? If anyone need clarifications, you can ask from me. So I'll be here up to 12 p.m. So it's better to finish this now. And so if you get any questions, so you can ask from me if you face any problem with the simulation. So the lecture is completed. Now you have the time to work on this task and find out the dynamic losses for this DC example as well as for the switching example. So this will lead you to get some one step forward in your power electronic design, which will help you to when you moving forward in industrial environmental. This kind of calculations is really important. All right, so feel free to ask any questions and start working on this now.